Now let's look at how to explore performance-based database design. You can use the link here on the screen if you'd like to follow along. Database design is an important aspect of database performance, even though it's not always under the control of the database administrator. You may be working with third-party vendor applications that you didn't build. Whenever possible, it's important to design your database properly for the workload. Whether it's online transaction processing production database like OLTP, designed for very fast transactions like insert, update, or delete, or an online analytical processing data warehouse designed for fast queries with select. Many design decisions, such as choosing the right data types, can make a large difference in the performance of your database. In this section, we'll explore a normalized database design and some of its normal forms. We'll also assist in choosing the appropriate data and index types for your data. Database normalization is a design process used to organize a given set of data into tables and columns in a database. The normalization process has been around for a very long time. There are many books, seminars, quarter and semester-long classes, videos, articles, and more that you can use to learn how to normalize your database. We're only going to scratch really here the surface. This section is a very high overview of getting your data into that third normal form. The first normal form in database normalization, which is a foundational step in organizing relational databases, is to reduce redundancy and improve data integrity. It emphasizes three key principles: creating a separate table for each set of related data, eliminating repeating groups within individual tables, and identifying each set of related data with the primary key. The example table here demonstrates how each product is uniquely identified by a product ID, ensuring that each row contains unique values without repeating itself. Database normalization is illustrated here. Helps to streamline updates and inserts, such as modifying a customer address in one place by ensuring that the data related to a specific entity is stored in a dedicated table. This design approach enhances consistency, reduces storage overhead, and improves query performance, making it especially beneficial for systems like inventory management or transaction-based systems, or customer relationship management platforms. The second normal form builds upon the first normal form by eliminating partial dependencies in tables with composite keys. In relational databases, second normal form ensures that all non-key attributes or fields depend on the entire composite key, not just part of it. This is crucial for maintaining ACID properties like atomicity, consistency, isolation, and durability by preventing update anomalies and preserving data integrity. For example, if we assume a composite key made up of product ID and product name, then all other columns must depend on both parts of that key to satisfy second normal form. However, attributes like price, production country, short location, all of those depend on product ID and not on the full composite key. This partial dependency violates second normal form and can lead to update anomalies. To resolve this, attributes like price should be moved to a separate table where product ID is the sole key, ensuring centralized and consistent updates. The benefits of normalization include reduced redundancy, improving data integrity, and easier maintenance, making it a foundational practice in relational database design. Use cases include designing scalable and reliable systems where consistent data updates are critical, such as inventory management, financial systems, and product catalogs, and more. The third normal form in database normalization builds upon the requirements of the second normal form by ensuring that all non-key attributes are non-transitively dependent on the primary key. In other words, attributes should depend only on the primary key and not on other non-key attributes, aka fields. The example table violates third normal form because the short location column depends on the production country rather than directly on the primary key product ID. This kind of design can lead to redundancy and update anomalies, making it harder to maintain data integrity. Normalizing to the second normal form and the third normal form helps reduce duplication, prevent update anomalies, and improve maintainability, especially for OLTP systems where data consistency and efficiency are critical. The denormalized database design is commonly used in data warehouses and data marts to reduce the number of joins needed for fast reporting, thereby improving query performance. This approach contrasts the third normal form, which aims to eliminate redundancy and ensure that all non-key attributes are non-transitively dependent on the primary key, promoting data integrity. While the third normal form is theoretically ideal, it may not be practical for all data sets, especially when performance is a priority. Normalized schemas often require multiple joins, which can increase CPU usage during queries. Denormalization, on the other hand, starts with a normalized database and selectively adds columns to reduce joins, accepting the risks of update anomalies. To mitigate these risks, developers use triggers or other mechanisms to ensure consistency when updating duplicate data. Use cases for denormalization include scenarios like frequently reporting OLAP systems, online analytical processing systems, where performance outweighs strict normalization, while OLTP systems typically benefit from normalized designs to maintain data accuracy and consistency. Data types can be used in optimizing database performance. Here are a few best practices. Remember to align database types between the application code and the database tables, avoiding costly implicit conversions that can lead to inefficient execution plans, favoring smaller data types to reduce memory usage, and leveraging data compression to further enhance performance. These practices help improve query efficiency, reduce CPU and memory consumption, and minimize storage overhead. Use cases include tuning SQL queries, designing scalable applications, and managing large data sets in enterprise environments where performance and resource optimization are essential. Normal data types that use 1 byte per character are restricted to just 256 possible characters. This constraint necessitates the use of multiple encoding specifications or code pages to support different alphabets, such as European languages with relatively small character sets, and makes it impossible to handle complex writing systems like Japanese or Korean, which contain thousands of characters. Each SQL Server coalition includes a code page that defines how bit patterns represent characters in char, varchar, or text values, and these can vary across columns and client systems. This variability introduces significant challenges when building international systems, as developers must carefully select code pages that meet language requirements for multiple regions, and it ensures accurate character translation across systems. To overcome these issues, SQL Server supports Unicode data types. These use 2 bytes per character, enabling representation of up to 65,536 patterns. And this is essential for supporting Cyrillic, Asian languages, and other languages with a wide range of symbols. This makes Unicode data crucial for global application that requires consistent and comprehensive multilingual support. Here we see some of the many different types of database indexes that enhance query performance: data integrity and storage efficiency. A clustered index sorts and stores row data based on the index key, allowing fast range queries but limited to one per table. A non-clustered index maintains a separate structure with pointers to data rows, enabling quick lookups and supporting multiple indexes per tables. A unique index enforces uniqueness in the column values, preventing duplicates and ensuring data integrity. A filtered index applies a where clause to the index only to work with indexing a subset of rows, reducing overhead and improving performance for targeted queries. A full text index supports advanced text searches across large character-based fields, and a spatial index is optimized for querying spatial data types like geometry, geography, and it's useful for mapping and geolocation applications. And then the XML index accelerates queries on XML columns by indexing paths and values with that XML structure. Lastly, a column store index stores data in a columnar format. This is ideal for analytics and data warehousing due to its high compression and efficient scanning capabilities. These indexes are vital for optimizing query execution plans, reducing I/O, and improving scalability across transactional and analytical workloads. Here are some best practices for creating efficient indexes in SQL Server to enhance query performance and storage efficiency. Clustered index keys should be narrow and carefully chosen to minimize page splits, improve data locality, and reduce disk seek time. For non-clustered indexes, placing the most selective column first and using include columns helps to maintain narrow and high-performing keys, although consider too of placing the equality fields in the composite non-clustered index and the inequality fields in the include clause, as we have found that to be a best practice to help speed up our query performance. Also, avoiding redundant or unused indexes is crucial to preventing unnecessary overhead. SQL Server supports various index types tailored to different workloads, such as clustered, non-clustered, column store, and full text indexes. At a high level, an index enables SQL Server to locate rows based on index keys composed of one or more columns, far more efficiently than scanning the entire table. These index strategies are especially beneficial in OLTP systems where fast data retrieval and minimal resource usage is critical. A clustered index sorts and stores the actual data rows in a table based on the index key, making it the physical structure of the table itself. Because data can only be stored in one order, each table can only have one clustered index, which can be a composite if you'd like. While often aligned with the primary key, the clustered indexes do not require uniqueness. A common DBA interview question is to distinguish clustered from non-clustered indexes, which maintain a separate structure with pointers to the data rows and allow multiple indexes per table. A table without a clustered index is called a heap, where the data isn't kept in any particular order. For optimal performance, the clustered index key should be narrow, unique, and frequently used in sorting and sequential access patterns. This design minimizes sorting overhead and enhances query efficiency. Some use cases include tables with frequent range queries, large data sets requiring ordered retrieval, and scenarios where sorting performance is critical. Benefits include faster data access, reduced I/O, and improved query execution plans. SQL Server uses non-clustered index as secondary structures to enhance query performance, especially for queries not efficiently handled by the clustered index. These indexes store key values and pointers to the actual data rows, allowing SQL Server to locate data without scanning the entire table. You can create multiple non-clustered indexes on a table, and you can use the Include Columns feature to cover more query columns at the leaf level, improving performance without really bloating that index key. Filtered indexes are particularly useful for tables with large data skew, targeting specific subsets of data, while non-clustered indexes improve read performance and query efficiency. They come with trade-offs such as increased storage requirements and overhead during data modifications. They're ideal, however, for OLTP systems where selective queries benefit from fast lookups, but careful design is needed to balance performance gains with resource costs. Here we see the structure and function of non-clustered indexes in SQL Server, highlighting how they enhance query performance by organizing index nodes in a B-tree or balanced tree format. Each page in the index is an index node, with the top node called the root node and the bottom node forming the leaf level, which ultimately points to the data rows on that data page. Unlike clustered indexes, non-clustered indexes do not alter the physical order of the data, but instead maintain a separate structure with pointers, allowing multiple indexes per table. This design supports efficient querying across different columns and is especially beneficial for read-heavy operations. However, index design involves trade-offs. Narrow indexes with fewer columns are faster to update and require less maintenance, while wider indexes may support more queries but incur higher overhead. The query optimizer selects the best available index, but experimenting with different designs can uncover better performance options. Use cases include optimizing search conditions, supporting multiple query patterns, and improving performance in applications with complex filtering or sorting needs. In a column store index, SQL Server stores data in columns rather than rows, enabling high compression rates and reducing storage and memory usage. This column-based structure allows SQL Server to scan only the columns referenced in a query, significantly lowering I/O operations. Column store indexes are especially beneficial for large tables such as data warehouse fact tables and temporal history tables. Clustered column store indexes include all columns in the table and are ideal for DW data warehouse workloads and the fact table, while non-clustered column store indexes support real-time analytics in OLTP environments. More broadly, SQL Server offers various index types, clustered, non-clustered, filter, and column store, to support different workloads. At a high level, an index is an on-disk structure tied to a table or view that helps SQL Server quickly locate rows based on index keys, avoiding full table scans and improving query performance. Let's see the performance advantage of using clustered column store indexes over traditional clustered indexes with page compression for bulk data loads. Here we see that we compare the time that it's taken to insert over 1 million rows into a table. One is using the clustered column store index, and the other is using the clustered index with page compression. The column store index completes the operation in just 8 seconds, while the page compression index takes 20 seconds. Column store indexes store data in a columnar format, enabling high compression and efficiency querying for large data sets, especially in a data warehouse workload. A key benefit is that their optimized load path for bulk inserts of 102,400 rows or more, which are directly loaded into memory as row groups, with collections of up to approximately 1,024,000 rows. Fewer full row groups improve select query performance by reducing the number of row groups scanned. Smaller inserts less than 102,400 rows are temporarily stored in a B-tree structure called the delta store and asynchronously compressed into the column store. Use cases include analytics, reporting, ETL operations, and any place where we have a high volume data ingestion and fast query performance when they're critical. Now it's time for our knowledge check. Number one, what type of database design should you use for a data warehouse when you want to reduce the data volume of your dimensions? Answer, Snowflake schema. Number two, what is the minimum number of rows you need to bulk insert into a column store index? Answer, 102,400. Number three, which compression type offers the highest level of compression? Answer, column store archival. Now it's time to take a look at how to identify database design issues. Now let's take a look at lab number 9, identify database design issues. And we're going to start like we've started a number of our labs, and that is by restoring the AdventureWorks 2017 sample database there. And so this should get us started. Now this lab is going to focus on trying to identify why our queries are running so slow. So we're going to focus on the design aspect of it right here, and we're going to make some changes. We're going to add an index. We're going to change the design a little bit. And should that make it run faster? We'll take a look. This is really the question that we're going to try to answer in this section. So with this restored, what I'm going to do is I'm going to open up a new query window here, and I'm going to paste in one of our queries here from our lab. And that's selecting these 5 fields. As you can see, business entity ID, national ID number, login ID, hire date, job title from the employee table and human resources schema in our database AdventureWorks 2017. And we're looking for where the national number ID is that long number that you see right there. So before I run this, I'm going to go ahead and turn on our include actual execution plan. Now you can add some additional options if you like. This will give us some more information. The live statistic queries is really good. You'll also see here that you can include the client stats if you need to do a little bit more in depth and why the query is running slow. So we're going to do it here with what we have right here. And this is including the actual execution plan. And I'm going to go ahead and execute this, and then we're going to see the result. And the only one, actually, yeah, it took about 2 seconds to run the results, which seemed like a long time. But let's try to investigate why this could have happened. So this is the result tab where we have the message. And we can see here it gives us a little extra information about what happened with the execution plan. Now this execution plan, when we take a look at it, you can see that it did essentially a clustered index scan that is usually done when there's either, you're having to parse a lot of records or there's no viable indexes for it to use to run the query. It just has to scan all the records to get the results it wants. And given that it took so long, I'm assuming that what it did is that's what it did. But I want to also note here, there's a little yellow triangle that you might want to do a little bit of a deeper dive into. So I'm going to go ahead and click that yellow triangle right there. And it's going to give me some extra information. The cash plan size, estimated operator cost. You can see also the warning down below. So it had to do a type conversion in the expression. It had to do an implicit conversion. There was an integer. So there might be a little bit of an issue here with one of the fields. So maybe the national ID number we want to take a little closer look at. And if I set my mouse over my execution plan, and reading from right to left, top to bottom, you will see that it had to scan about, how many rows? 383 bytes in each row and 290 rows. So it had to read through all those and look 2 seconds to retrieve one record. Seems like a really long time, but I think the issue is where that little triangle is at. So something with that field national ID number where we have it in our where clause here. So there might be a little bit of an issue. So what I'm going to do is I'm going to go take a look at the human resources employee table and see if I can spot anything. And I can zoom in, or if I'm finding it here, I should be able to see it off to the right. If I refresh databases, we could go do it out here and find it. But we do have it in the lab kind of already listed out. So I'm going to go ahead and show you what it looks like. And the national ID number is nvarchar. So that could have something to do with this, especially because our query, when we go back to the query, it doesn't look like it's character. It doesn't look like a character field. So it must have treated it like an integer. And so then it had to do that conversion to the implicit conversion to nvarchar. So it actually should be, inside of quotes if we want it to actually be character, to have it not do the conversion anymore. So we're going to rerun this. We're going to re-execute this and see what it looks like. One record retrieved in under 1 second. And then we have this issue now. So we fixed one, but it looks like we have another. And so we have to go to little yellow triangle. Has it gone away? The little yellow triangle has gone away, but you can see the query as we look at the execution plan is actually doing a little bit of an index seek here. So it's using one index that's available in our list there. And we could take a closer look at that as it goes through. So it decided to use an index, and there's an index on the national ID. And you can see that under the object, right? Oops, the object. If you go down a little bit lower than my arrow, you can see the object picks up the national ID number so that there is the index and it's doing a seek. So it's picking it up. That looks good. But then it does a key lookup, and the key lookup is really bad for performance. So now, granted, right now this is taking less than a second to run. We're retrieving one record, and it's a very small table. But what you need to remember is that this table, if we're planning on it growing over time, it's going to run slower and slower. So it may not be an emergency to fix it right now, but these key lookups are really bad for performance. And how we fix the key lookup is we need to adjust the index. So we might want to eventually around this do a non-clustered, composite non-clustered index. Then it has this nested loop, and we've got to figure out if we want to fix this key lookup, and we can do that at the very end here. So what we're going to do is we're going to try to do this by going to alter the table and right now and see if we can fix it with the nvarchar to make it more of an integer, because this might help its performance also. But when we execute this, we get an error. And the reason is because there is an index already there on the table, and you can't just come and alter an index. It's going to affect it. So what we can do, one option is we can go in and we can drop the index and then change the table so that we can adjust that national number as an integer. That's one option that we can work with here. And then we can also recreate the index and add the unique index back in there. So we're going to go ahead and run this. And there's no alter index. So you have to drop and create in the same statement here. And then we're going to execute this. And then we're going to test our query again. So let me paste that query back in, or we can go back to our other tab here and try to find it. Well, we're going to do it. Let's see if the data type has changed now. And we'll click that query. And we'll try to follow this again. We've changed the data type. And yes, it's been changed to an integer. And now we'll go back and run the same query again. But this time we'll run the query, if I can find it here. And we'll do it in single quotes because we just adjusted it to an integer. And let me see if we can get the same results that we see down here. So let's execute that query again, and still under 1 second to run it. And the same execution plan from it. So we lost that error, but at the same time, we did get the execution plan to stay the same. So I'm going to add something to this to get rid of that key lookup, which may at long term be very costly. So this is not in the lab, but I do want to show that this is what you can do. You can use the include statement. So let me copy this and paste it here into our query window. And I'm going to run the same commands, but I'm going to drop the index. And this time when I make it, I'm going to use the include statement. So the national ID number will still have the index on it. And we're going to include the fields that were in our select clause. So if I create this new index, which is a really good way to make an index, we don't usually just want to have an index on one field. We want to index also to include the fields that are commonly queried for. And that would be what's in our select clause. So I added it here in the index in the include statement. So now when I run the query, if I can find it one more time, let me see if I can find it. Actually, the number 2 here. So let me see if I can pull it back up. And when I run the query, we're going to get an index seek, I hope. And there we go. So an easy way to do it here. That's going to pick this up. So as the table grows, this is the best index to have. And when you think about creating an index, you want to include the fields in the index that are those in the select clause. You also want to include anything in the where clause. And foreign keys, all of those are really good to use here. So usually when we go through the employee table, we find the worst performing queries. You can try an index too to hopefully make it run faster. Usually a composite, non-clustered index is the best to do. And as we look at the queries, there's the select clause, the where clause. All these fields are candidates to include in your index. And then what I do is I also look for maybe the 10 top worst performing queries, and maybe there's 5 fields that they have in common. And then what I look at then is I look at which fields out of those 5 are the most unique. And then maybe I try to weed this down to just maybe 4 fields that are highly unique, and I use those in my index here. So there we go. Let me see if I can find this. It should actually be the last one in the list here. So I can put those in the include clause. So hopefully this gives you a little look at how you might want to approach indexing. And we don't usually need to index if it's a small table, but if the table is going to be growing over time, you want to implement best practices from the very beginning. Now let's take a look at our next section, Evaluate Performance Improvements. Please follow along if you'd like to with the link provided here on the slide. One of the challenges of the DBA's role is to evaluate the changes they make to code or data structures on a busy production system. While tuning a single query in isolation offers easy metrics such as elapsed time or logical reads, making minor tweaks on a busy system may require deeper evaluation. In this section, we will do a deeper dive into index tuning. Also, we'll explore query hints, and we'll take a look at weight statistics. Weight statistics offer a powerful method for monitoring SQL Server performance by analyzing what each thread is waiting on. SQL Server Weight Tracking System logs wait events for every running thread, helping database administrators identify bottlenecks related to hardware, configuration, or inefficient code. This data is stored in a dynamic management view, one like our sys.dm OS wait stats and sys.dm DB wait stats. Both of these are related to Azure SQL Database, and active session wait times can also be tracked through sys.dm execute session wait stats. SQL Server tracks over 900 wait types. So these were just a few that were mentioned. Those wait types are categorized a few ways. One is a queue wait. A queue wait occurs when a worker thread is idle and it's waiting for a worker to be assigned. The resource wait occurs when a worker thread in SQL Server requests access to a resource that is currently being used by a thread. Examples here are that resource waits are locks, latches, and disk I/O waits. Example queue waits are deadlocks, monitoring, deleted records, cleanup. All of that can happen for a queue wait when there's a deadlock or a deleted record cleanup. And then external waits occur when SQL Server is waiting on an external process like a linked server query to complete. An example of an external wait is a network wait relating to returning a large result set from a client. These statistics are persisted for instance startup and can be flushed to observe performance changes over time. The benefit of using wait statistics is that they provide a holistic view of server health, allowing DBAs to pinpoint and resolve performance issues efficiently. This approach is especially useful in diagnosing slow queries, optimizing workloads, and ensuring system responsiveness to both our OLTP and OLAP environments. Here are 4 common SQL waits. Resource semaphore waits occur when queries are stalled waiting for memory, often due to excessive memory grants. Monitoring this helps the DBA fine-tune memory allocation and improve query performance in memory-intensive workloads. Our lock-MX wait, that indicates blocking issues caused by long transactions or poor indexing. You can resolve this through better transaction management or switching to the read committed snapshot isolation level, which will enhance concurrency and throughput for high transaction environments. Another wait is our page I/O latch wait. This wait suggests inefficient indexing or slow storage performance, especially when SQL Server scans large volumes of data. So optimizing indexes and improving disk I/O are critical for read-heavy workloads in this scenario. SOS scheduler yield, this type of a wait reflects CPU pressure from high workloads, or usually it is a missing index or a suboptimal query structure. And we want to address these waits through workload balancing and index tuning improvements. These wait types are tracked via the sys.dm OS wait stats, which gives us a holistic view of our server health and are essential for proactive performance tuning here across our diverse SQL Server use cases. Here is a 4-step process for optimizing SQL Server performance through effective indexing. It begins with identifying expensive queries using tools like the query store or extended events profiling, followed by examining their execution plans to uncover inefficiencies. Next, testing index changes to measure improvements in I/O and elapsed time. And finally, implementing validated changes in production. This approach is especially beneficial when tuning T-SQL queries, as indexing strategy is one of the most effective methods for performance enhancement. Properly indexed databases reduce I/O operations, alleviate pressure on storage, and improve memory utilization. It's crucial to consider the read-write ratio of the database. While heavy write workloads may not benefit from additional indexes due to the write overhead, workloads with frequent updates that involve lookups can gain from added indexes or include columns. The goal is to maximize performance gains with the fewest necessary indexes, ensuring efficiency without compromising update performance. This methodology is ideal for OLTP systems, reporting environments, and any workload where query responsiveness is critical. This process is also an ongoing process. Now we see a structured approach to optimizing SQL Server indexes for faster queries with minimal I/O overhead. It emphasizes evaluating current index uses via system views like our sys.dm DB. There's an index operational stats you can use and an index usage stats, and then removing unused or duplicate indexes, and then analyzing costly queries from the query store or through extended events, and then testing new indexes in non-production environments, and finally deploying them to production. A key challenge to address is index fragmentation, which occurs as data is inserted, updated, or deleted, and this causes the logical order of the index entries to diverge from the physical layout. This fragmentation scatters data across pages, forcing the data engine to read more pages to locate the records, thereby degrading query performance. Regular index tuning and maintenance not only improve query speed and resource efficiency, but also ensures that indexes remain aligned with our evolving data patterns. So use cases here involve performance optimization in transactional systems, analytical platforms, and any workload where query speed and resource utilization are crucial. It is important to manage index fragmentation in SQL Server to preserve query performance. As data is inserted, updated, or deleted, the logical order of the index entries can diverge from the physical placement on the disk pages, leading to fragmentation. This scattered data layout forces the database engine to read more pages to locate the relevant rows. This increases our I/O and degrades performance. To address this, SQL Server and Azure SQL Database support regular index reorganization and rebuilding, including online and resumable operations in newer versions. Fragmentation details are tracked in the dynamic management view here, listed as sys.dm db index physical stats. This helps the database administrator to assess and to maintain index health. Proper index maintenance is especially beneficial in high read environments, ensuring efficient data access and reducing resource consumption. Index maintenance outlines two essential strategies: reorganization and rebuilding, for preserving index efficiency and optimizing SQL Server performance. Reorganization is an online process that defrags indexes by reordering the leaf-level pages and compacting them based on the fill factor, while rebuilding drops and recreates index pages. It updates statistics, and it's recommended when fragmentation exceeds 30%. With options for online or offline. These maintenance actions are crucial for reducing input-output operations and improving query performance, especially in read-heavy environments. A well-tuned index strategy, selecting the fewest, most effective indexes, minimizes storage and maintenance overhead. It enhances memory utilization and balances performance across read-write workloads. For write-intensive systems, fewer indexes reduce the cost of insert operations, while update-heavy workloads may benefit from additional indexes or columns to support lookups. The goal is always to achieve the greatest performance benefit with the smallest number of indexes, making index maintenance a foundational practice for scalable and efficient database systems. Don't forget to work with the column store index maintenance, as you will need to monitor and manage fragmentation in the column store index with SQL Server. So unlike B-tree indexes, column store index fragmentation is not reported in the same way and is primarily caused by delete and update operations that leave behind deleted rows. These rows, while excluded from the query results, are still scanned during execution, leading to unnecessary I/O and degraded performance. A practical metric for assessing fragmentation is the percentage of deleted rows. If 20% or more are deleted, it's advisable to reorganize this index. This can be evaluated using a dynamic management view, the sys.dm column store row group physical stats, and you can do this in a test environment. It's beneficial to verify whether reorganization improves the workload performance, though, after you've done it. Column store indexes are especially useful in large data warehouse tables and in real-time analytics scenarios where maintaining optimal performance through regular index maintenance is critical. Query hints are directives that enforce specific behavior across an entire SQL query, influencing all operators involved. These hints are especially valuable when the query optimizer cannot resolve performance issues through its default logic, offering a manual override to guide execution strategy. Common use cases include limiting memory grants to prevent excessive resource consumption, forcing the use of particular index to improve lookup efficiency, and controlling join behavior to avoid suboptimal plans. The benefit of query hints lies in their ability to fine-tune query execution when conventional tuning methods fall short, making them a powerful tool for database administrators and developers who need to manage complex and unpredictable workloads. Here are 3 commonly used SQL Server query hints. One is force seek, which directs the optimizer to use an index seek instead of a scan, improving performance for selective queries by reducing I/O. It's beneficial when the optimizer chooses a scan, but a seek would be more efficient, especially in large tables with well-defined indexes. Another one is optimize for, which tells the optimizer to generate a plan assuming a specific parameter value, which helps avoid parameter sniffing issues. This is useful when queries perform inconsistently due to varying parameter values. And lastly, max DOP. This limits the number of processors used for parallel execution for a query, helping to control CPU usage. It's ideal for managing performance in high concurrency environments or when parallelism causes excessive resource consumption. Now it's time for our knowledge check. Question 1, what type of index is best suited for a data warehouse? Answer, clustered column store. Question 2, which DMV provides information about server-level weight statistics? Answer, sys.dm OS weight statistics. Question 3, which DM can you use to capture the actual execution plan for a given query? Answer, sys.dm execute query plan stats. Now let's take a look at how to isolate problem areas in poorly performing queries in SQL Database. Welcome to lab number 10, Isolate Problem Areas in Poorly Performing Queries, here in a SQL database. Now we find ourselves back in the Management Studio, and I already have our AdventureWorks 2017 database we're stored here, and if you'd like to, you can follow along in the lab here. So some of the things that we're going to show you here is a query that we can run that we ran a little bit ago, actually in our last lab, but we're going to highlight it here and another aspect of it here. So you might remember we have this national ID number that is actually what it was. It's a non-varchar. So what we want to do is we want to work with it here. So it has character data, and we want to execute this and show the plan. And what we're going to do is we're going to see a little bit of the processing of what it goes through. But in particular, we can take a little bit of a closer look. And there is our select statement. By dragging this one out a little bit, let me see if we can get the full statement, and it shows a little bit about what it did. And what I can do is I can scroll to the right to see more information on it here. So it's trying to show us what it did, and we can see how something like this would run. And we have a good option here to do the show plan all. It's kind of a text version of your query plan. So it's this one right here, and you can go into the messages here and you can see how long it took to complete. But one of the things I'm going to add to this is I'm going to run this one more time, but I'm going to put it on the actual execution plan, and we might be able to get some information from there too. And when we run this, I hit the wrong button there. Let me make certain that I have the actual execution plan hit to execute it this time. And when we see if we can get that actual execution plan to show up, now what we can do is I believe we have it to show right here. So that's something to note, that this is going to be our actual execution plan. It's going to show it to us here. So I'm going to run it again, and I'm going to run it with just running that one statement. And let me see what it looks like here. Here's the execution plan. So we have one where we saw the execution plan in text, another where we see it right here graphically, but this is available here through the actual execution plan versus the show plan all. So you can choose the one that you want to work with here, which one you want to see. They both look pretty good. The other thing I'm going to note here is that we could also look at a suboptimal query plan here. And we're going to do a number of these to resolve this and see what we get. So we're going to resolve for a suboptimal query plan. Here's the query that we want to look at. And when you take a look at this query, you can see that it's actually asking for a lot of fields. And we're talking about 6 fields. And we're also filtering out by date here and by product ID for the sales order. Details table there. And we've turned on statistics, IO, and time. That's some additional options you can add. Some of the set commands are very helpful, and we'll get a little bit more information when we run this. And when we do that, what we see is it's extracted 84 records, actually pretty fast. The message here tells us how it read the information. So it had 687 logical reads, but it had to go out and read about 12 pages off the hard disk. So not the best for performance long term, but it did it very quickly here. These reads are essentially pages. Recall that your information for your tables are stored on 8K pages, and those are usually going to be on the hard disk. And then once we query for that information, it takes it from the hard disks and puts it into cache, into memory. And then from here is where we can read it, and you can see that a lot of it was gotten out of cache, the logical. It was read into, from the physical into the logical area there. So I'm going to run this one more time, and I'm going to turn on the actual execution plan to execute that one more time. And we're going to see if the execution plan has any changes to it. And you can see how it looks. And we can also do something very similar with this if we, can make a few adjustments here where we work with the include statement. So remember that when you see this key lookup like this is a bad scenario. And the index seek is good, but having to go into the heap and retrieve our data so that we can get the 84 records back to us in our query is really slow. Notice only 1 second that it took to retrieve it. But note too, if I can set my mouse on this, I can get and open this window up here, and I can get a little bit more about the records that it had to read. It's a filtered version of it. It took 1 second to read 221 rows. We're estimated number of rows to read there. We could also optimize this a bit. And one of the ways, if you remember, is to kind of get rid of that key lookup there and make some adjustments to the index. So we're going to go do that and go ahead and create another window here. And this is from our lab also. So we're going to create and drop in the same statement a new index. Create and drop an index, make a new index. Now I want to note here that we have the index product ID, and we're going to put the index on the sales order details table, on product ID, on modifying date here. So they're going to work with 2 fields here, and for some reason it's only including 2 fields for this. So of course it has to be the most unique that we're going to work with here. So they have to use those indexes on those fields, and then we're going to add this in. So the carrier tracking number, the order quantity, and the unit price. And if we go back to the query, we can also put this on a couple fields. It's going to be on the product ID and modified date. So they picked up a couple here, product ID, modified date. And note too that this is included, what's included in our select clause is good to add here. So we've added here, and then we're going to go ahead and run it. And then once we add this new index, let's take a look at the statement one more time. Let's make certain that we have the actual execution plan, and we're going to execute it one more time. And again, it's under a second to retrieve the records. And what we get here is just our index seek, which is what we wanted. So those composite non-clustered indexes work out really well. So you can go out and figure, is this worth taking the time to create or not? You have to decide. It took it 1 second to retrieve 84 records, and it's not likely worth our effort. But over time, if this table, sales order details, is going to grow and grow and grow and grow, and as it likely will, these queries will run slower and slower and slower. So we need to consider best practices when we first roll this out. And so this is a field here in the table that you might want to consider putting your indexes on using the include statement. And it's definitely one thing to consider over time. And we're going to have to adjust these indexes as the queries change, of course. And maybe as our tables become less selective, less unique, we might need to adjust the indexes too. But we have a few options. So we have that to look at. Looks pretty good. Now, one of the other things that we have here in our lab is we also want to take advantage of our query store. And so we're going to go ahead and paste in this right here, and the query store is going to be turned on, and the operation is read write, and they're setting it to, it works with really old compatibility levels, and one that was roughly around in 2008. Now, what we're going to do is we have lots of newer SQL versions here that we could work with, but we have more options for making it run faster with the newer versions than the previous version. So that's why we're making it act like 2008. And we're doing that so we can see maybe a few more issues with our queries than we would normally see with some of the newer versions. So that's why we're going with that older version. And we can adjust it back in a bit too. Now there's a number of files that we want to use with this. So I'm going to go ahead and run at least one, actually 2 of them. I'm going to open this one first. This is I'm going to hang on when I open this. I think I'm going to do it here by opening it in the Management Studio. So this is one of our lab files right here. And this is one that we've opened up for using here. And I'm just getting these out of the lab. This is part of our lab. All the lab files are number 10. I'm going to open up another one in a moment here. And then we'll create for us some tabs here in the Management Studio, which should hopefully be easy enough to do there, is adding these in, query tabs. And then I'm going to go ahead and I'm going to execute the workload on the first one, which I believe, let's see, it should be a random one right here. And it's pretty random. There's a bunch of select statements that are going to be run. It'll take a while to run this list here. and I will go ahead and execute that. I'm actually going to turn on the include actual plan first. And here it is right here. And it's going to take a moment to run. It looks like it's about, maybe 7 seconds there or longer. And it's going to take a little bit to execute, and we'll execute that here. So let's go through, and it might take a little bit to run. So, okay, it's about 15 seconds. And I'm going to go into the execution plan and see that it was quite a number of things that it did. So it did an index seek, it did filtering, it did a key lookup, it did a nested loop, another nested loop here. They aren't so bad. It's the key lookup that is the issue here. So I'm showing what it went through, and there could be another option, and we'll add them. And this is another query here where it's going to do a lot of parameters inside. And as you can see, it really is just trying to create a ton of work in here. And so this is another random workload, honestly. I have the execution plan that I'm going to turn on here, the actual one. And I'm also going to turn on include live statistics. And this will make it very interesting. So I'll execute this one, and it will take a moment. And this one actually ran pretty fast here. And you can see that it's still executing. And we can go through the various tabs. The live stats is where it's where we're at right now, and it's showing you as it's going query by query. And there's a lot of queries that it's running. And it runs each of the queries. It will display how it's executing the information or extracting. So that's interesting. I could also look at the execution plan, and we can see the plan there too. And there's one that's run. It took up to 31 seconds right now. But all of this, is running like it's 2008. So we definitely have some new options that we can use here that if we want to try to see. So I'm going to go ahead, and we just wanted to really see some activity there on our query store is really why we ran these, to get some activity into it. And it looks like it took about 56 seconds to run. And as I go through, you can see every query of the execution plan here, and you can there's a lot really to look at as you go through. One execution for each query that it ran, and you can see the messages, and you can see the rows that were affected. So it's a varying number here that we're looking through. And then the results on this, you can see a little bit more in there of what it's actually extracting. Here's the show plan all that we had enabled, so you can get a lot of detail from this. I can drag it down, and you can take a look at what it extracted. It gives us a little plan for each. I kind of like the live query statistics. The execution plan gives you a lot more detail there too. So I really enjoy that. But what we're going to do is we're going to go ahead, and I think it's still executing. So we'll let that run, and I can see it right there. It's still executing. And I'm going to do a new query where while that is running, and I'm going to change it up like it's a little bit more current with 160, which is essentially SQL Server 2022. So once we change the compatibility level to that, we have a lot more options. It should be a lot faster to run. And then what I'm going to do is execute this, and it should be fairly fast. And then I'm going to go into the query store. And now this query store, I'm going to find it here on 2017. And I'm going to see that option here, the query store, if I can find that. So it should be, let's see, should be a way to get into the view there. It's under management. Yeah, I thought it was broken out separately, but here it is. Okay. It should have been maybe under database. So we can take a look there. And if we go into it, let's see, maybe it just needs to be refreshed. And that's what it is because it's under database. Actually, let me refresh it, because we just turned it on. So there it is. I can run the command. Well, it ran it a little bit ago. Maybe it didn't run, but I thought I did. So we'll go back to that. We'll see if it's there. Oh, I forgot to run it. Okay, so that could be why. So let's run it. Let me execute this. There we go. And then let me refresh, and it should be under database. And there it is. Okay, so we have it. Okay, perfect. It showing you things that you can do to show this up. And then now we're going to come in and we're going to look at the top queries consuming resources. And that will open up our query store. Take a look at it. And now the issue that I'm going to have is I'm going to have to return to the query a little bit because it doesn't have that much data. And I'm just going to run these one more time. So we do have to do this in a certain sequence here. Run the query store to make it open, and then go back and run the queries. So we'll do that. We'll execute this one more time. We'll get that set up. It's going to be really kind of a big resource using different types of queries here that we'll see. And we just run that one more time. And we'll let that execute. And then I'm going to go out to our random one. It's a pretty nice one, really involved one. And we'll run that one more time. And we'll get the query store to pick it up. So we'll let that run a bit. And let's see how that works out for us. And we'll go and we'll spend a little bit more time running this query, taking a look at it. And it executes pretty fast. It's been running for a little bit there. I'm going to refresh the query store that I turned on. And then I'm going to go into the top resource consuming queries there and take another look. And let's double click. And yeah, now we have some information. And so it only has one query here so far on the plan, but you can configure this to have a bit more added to the plan if you'd like. You can pick how many plans you would like to have it run by adding in that number there. And so it's going to give us a little bit more detail. Let's get it running here. It might take a moment for it to kick in. I'm going to check to see. We've applied the 2 there. And we'll see that there. So it could be that we have a big query running in the background. And that kind of takes a little time for it to refresh. I will open it one more time there. I'll refresh it right here and see if we can get it to show up. I'll close it and I'll refresh this. And then in the background, we'll see if we can get this to open again. So, but you know, this is part of what happens a lot of times. You want to work through it takes a little bit to show up here. So we'll go back in here. We'll configure this option to a 2 again. And we'll see what we get with that too. We'll click OK and see what we get. So I might have to stop this other running option right now because I think it's weighing this down. Yeah, I might have to do that. So I think this one, nope, this is the one that's done. And I have another that's running. And we'll see what we can get this to show us here in a moment. Try this one more time. I'll refresh this. We'll go back into it. I'll double click it. See if we can see the plans. Okay, so that looks a little bit better. We might have to finish this just a little bit with a timing issue. So it's showing us one of the 2 plans at a time. So it does take a little bit to open up there. And it gives it to us. Yeah, I think it might be having a little bit of an issue displaying the 2 plans right now. I'm just going to use the 1 plan for right now. But it should be able to show 2. I just think it's a little maxed out right now with resources. So just 1 plan for right now. We can see the plan. We can switch to the other plan. We should be able to do that in that little button up at the top on the right there, where it says Plan ID, middle right there. But you get the idea with this. It's going to show us what it's captured, the information that it got, and you can force a new plan if you like to over an old plan for the last known good if you'd like. And it can do that automatically if you remember. But this will give you a little bit more detail about what it's found. And we have the window here. We can see some of the resource that it's making available with running the query back there. We can also have that now. And what I also want to show is a little bit of our query hints too. So we saw the query store but we can force SQL to do what we want it to do with our query hits. So I'm going to go ahead and paste in our query hint, our little query here, and look at the execution plan first. And we'll run that. And we're going to look at the execution plan right now. So let's see, this is still running a little bit. There's the execution plan. And notice it has a key lookup, and it extracted 130 records. And it took a while to kind of make that happen, to retrieve those 130 records. And the messages here show you a little bit about the rows, some of the information that it had to go through to get this information back. Now we're going to do this, and I'm going to go in, and I'm actually going to do this with another query window and keep it separate here. I'm just going to run this query, but I'm going to go in and run it again with a different number. And run this session here. So rather than looking for 288, I'm going to have it look for 177. And I'm going to look at the execution plan. And the execution plan is looking at 277 and 288. The two are very, very different. So looking for 277 versus 288 is very, very different. And what we should note here is that, it's going to try to cache some of this information. It's going to try to reuse the query plan because it has parameter sniffing. But what we want to do is we want to force it to use a query hint, because maybe one plan is better than another that we want it to use. And when I have to use the query hint, what I can do is I can make it so that every time it runs this query, I can force it to redo the execution plan, because we don't necessarily want the same execution plan for both queries. So I can do a query hint to make this happen. So our best bet, and again, there's probably other things that we can do, not taking into consideration here those other things, I could tell it just compile every time, so that's an option. So if it's very inconsistent, it's usually because maybe there's a large table that has a lot of records inside of it. And maybe the most common query is something around that second option that we used. And then maybe the anomaly was the other one that we ran, the first one that we ran. So we can use query hints here to fix this. And what we can do is we can just tell it to do a recompile. So when you run this, figure out what's the best way to extract it and do it every time. And I'm going to have it adjust this. So normally SQL will do parameter sniffing, as I mentioned, and it will try to use the same execution plan over and over. But you can force it to not do that. I'm going to force it to recompile every time, especially if I'm getting inconsistent results with these different parameters. And like I said, I usually use this on a very large data set where maybe you have one number or a couple numbers where everyone searches for, and it uses that same execution plan. That works really well. But outside of those parameters, you have maybe really unique values, and what ends up happening is it uses the execution plan that it uses isn't efficient for it. So it's going to come up with drastically different execution plans. And then the execution plan is going to be, we want to tell it to recompile every time it executes. So we can use an option here if we're getting performance issues on one versus the other. And it's because it's doing that parameter sniffing. And there's an execution plan that it already has in mind to use, but it's not working really well for some of our anomaly parameters. So if it comes up and it's troublesome, what I can do is I can force it to recompile as one option to fix this. So that's when you have, like I said, a very large data set, values that you're looking for, like 99% of them are the same, but there's that 1% that are different. And you want to be able to recompile so that you can have that 1% run as efficiently as the other 99 does. So that's the idea. Okay, so I'm hoping this helps here, and you get a little bit of a chance to try out the query store and some of the options we see here. And note too, I can do that option recompile. That's our query hint right there. And you have the actual execution plan, live statistics, a lot of options to get a lot of detail. I hope this was helpful. And I hope too that you tune in for our next session. Thank you so much. For more information on SQL Server execution plans or monitoring performance by using the query store or query processing architecture, the guide, or even for index architecture and design, please see the references listed here. In this section, we evaluated performance improvements by first looking at weight stats, and then we focused on indexing, tuning, methodology, index maintenance, and lastly, rounded it out with query hints. All of these topics helped us to make sure our queries could run as fast as possible. I hope you enjoyed this section, and I'm looking forward to seeing you in the next. In this learning path, we first explored query performance optimization by understanding how execution plans are generated, how to interpret query plan warnings using the query store, and how to identify execution plan types, which are beneficial for diagnosing and improving slow-running queries. Second, we covered performance-based database design, including normalization principles, selecting efficient data types, and choosing appropriate index types to reduce redundancy and enhance query speed. All of this was useful for building scalable, maintainable databases. Lastly, we evaluated performance improvements through dynamic management views, weight statistics, and index statistic maintenance, enabling DBAs to monitor system health and apply targeted optimizations in production environments. Thank you for viewing this section, and I look forward to seeing you in the next.